waves. So there's a multiplicity of 8, and we really want to refer to just a closed back plane and say the indices, we are referring to the set of closed back planes which are crystallographically equivalent by using these curly brackets. Right? So square brackets refer to a specific plane, and curly brackets like this refer to crystallographically equivalent set of planes. Okay, now I said to you that this course will deal completely generally with crystals, not just metals. We might deal with a crystal which has 56 atoms. Yeah, so do you know an example of a crystal with a large number of atoms inside the unit cell? It actually happens in steels. Cementite, yeah? 56 atoms in the cell. So although it's very easy to draw this diagram here, which is body-centered cubic, it's no longer easy when you have a very complicated crystal structure. So my recommendation is you don't draw three-dimensional diagrams. They're not terribly useful as soon as you get away from the simplest of structures, because you need to rotate, look along different directions, and even then it can be confusing because of overlap. Yeah? This is called a structure projection. We are projecting along the z-axis here, and this lattice point is located at a height half, 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 right? We don't put the x and y coordinates because they are already apparent on the diagram, but we put the z coordinate. And when we don't put coordinates, that means there's a lattice point at 0 and at 1. Okay, so 0 and 1. Okay. So this is called a structure projection, and it's much, much easier to visualize than looking at something which is three-dimensional. So this is now a little bit more complicated. This is the face-centered cubic unit cell, where we have a lattice point at each corner and a lattice point at the center of each face. On the structure projection, it becomes very simple to look at. These are all at heights 0 and 1. So this is the face centering lattice point on the face parallel to the bottom. Okay, you can see 0 and 1. These are located at coordinates half and half upwards. For example, this point here. And these are the face centers of the vertical faces, basically. So this is the structure projection of the face-centered cubic cell. We also have a primitive cubic cell. Okay? And there are very, very, in fact, I know of only one metallic material which has the primitive cubic cell. It's polonium. Or it's not really a very stable structure otherwise. So most metals are either body-centered cubic, face-centered cubic, hexagonal, okay? And then you might get some with much lower symmetry. So these are the structure projections of the primitive, the body-centered, and the face-centered cell. So just as for primitive, we write the symbol P. For body-centered, we have the symbol I, because it's a German word for body-centered, which begins with I. Okay? And F is for face-centered cubic cell. So there are three varieties of unit cells for the cubic class of crystals. We also need to think about symmetry. We've already talked about that by identifying crystallographically equivalent planes and crystallographic equivalent directions. So in the cubic system, we had 6 cell edges, which all have exactly the same properties. If I change that to tetragonal, then the A axes are identical in the basal plane, but the C axis is different. So the symmetry changes, and now I have 4 equivalent 1, 0, 0 directions, not 6, okay? And so on. This is a mirror plane. So if I put an object like this, I will see another object at that location. This is a four-fold rotation axis. That means if I rotate by 90 degrees, then I will find an object like this at that location, and here and here. So a four-fold rotation axis is called the tetrad. I will come to that in more detail later. And of course, the very definition of a crystal requires translational symmetry, because the environment at every lattice point is exactly identical. Okay, so you can put your origin at any lattice point. So these are the basic elements of symmetry: rotation axes, mirror planes, and translational symmetry. There is another aspect which is a little bit more difficult to visualize. We will look at a two-dimensional visualization of this when we do stereograms. But basically what it means is that if I take this point and I invert it through the center, I find another equivalent point on the other side. Okay? So there is an inversion symmetry in this. Now, why is this important? If you don't have inversion symmetry, then the crystal acquires properties which are unusual. So if I stress the crystal, then I might displace charges in an unequal way, and therefore I will get the crystal charging up, and you might get a spark. Yeah? So that's ferroelectricity. So you know your lighters. In the old days, the lighters had a flint stone, which is a stone which you do that, which you strike and you get a spark. But nowadays it has a piezoelectric crystal, which when you hit will produce a spark, and that's the same in gas cookers. Yeah? You hear the click, click, click sound, that sparks coming out when you strike a piezoelectric crystal. So those will not have this center of symmetry. Okay? Okay. When crystallography first started, it was by looking at the beautiful shapes of crystals which you find in nature. Those crystals have had thousands and thousands of years to grow, and therefore they are close to the equilibrium shape of crystals. So just by looking at the symmetry of that shape, you could tell whether it's cubic or whether it's tetragonal or monoclinic or triclinic or whatever. That's how crystallography happened until diffraction and the Bragg law were discovered or invented around the early part of the 20th century. Before then, crystallography was by measuring the angles between faces of crystals. Very careful work. Yeah? Now, when you do that, when you measure macroscopic properties, you cannot, of course, make comments about the details of very small translations inside the crystal. Okay? So, for example, this is called a glide plane. This is a mirror plane. If I take this object and I reflect it, then I get this object here. Okay? So, if I have these two objects in my crystal, I know there's a mirror plane here. Yeah? There is another kind of a plane which is called a glide plane. So, if I take this and I reflect it along here and then translate it by a fraction of a lattice parameter, say half a lattice parameter, then I recover this object here. There's nothing left here. So this is a reflection plus a translation by a fraction of the lattice parameter. That's called a glide plane. Now, when you look at the macroscopic shape, this appears like a mirror plane, simply because you can't pick up that half a cell edge translation. Okay? But when you look at the details of the structure, you find the glide plane. Okay? But you need resolution on the atomic level. This is like a rotation axis, but in addition to rotation, there's a translation. So exactly like a screw. Yeah, when you turn the screw, it also moves, doesn't it? So here, this is a diode. That means 180-degree rotation. If I rotate it along here by 180 degrees, I have a shape like this, and translate it by a fraction of the repeat distance, and I recover this. Okay? So this is a screw axis. And when you look at the macroscopic shape of the crystal, that will appear just like a rotation axis. You don't pick up that very, very small translation. Oh, yeah? A screw and a glide? Yeah. So in this case, let's look at the screw first. So this is the screw axis, and this is the repeat distance. Okay? That means this is, I could start here or I could start here. Okay? Now, when I rotate by 180 degrees, it produces this. Yeah? And if I translate by half of the repeat distance, then it produces this. So this is an axis of rotation, right? It's a line. Okay. Now a glide plane is a plane, and I should really draw it as something like this. It's a bit tricky to draw, okay? But I'll draw black on this side of the plane and red on that side of the plane, right? So if I have this object here, then after reflecting, it becomes that object, okay, which is on the other side of the plane. And then I translate by a fraction. Yeah. So just reflection would make this plane a mirror. So a plane, a plane might have other objects here, which have to behave in the same way. Okay? Yeah, exactly. So a plane is two-dimensional, whereas an axis is one. The axis itself is, one-dimensional. Okay. Right. So we have, we can define all crystals into 7 different classes, right? And within each class, I have, for example, in the cubic, I have primitive, body-centered cubic, and face-centered cubic. So if I add up all the different varieties in these 7 crystal classes, I get the 14 different unit cells possible in 3 dimensions. Okay? And the cell is defined by the basis vectors. In the case of cubic, they are all identical in magnitude, and the angles are all 90 degrees. This is quite important, right? So if something, a triad is a rotation of 180 degrees, a rotation axis with 120 degrees. If you cannot find 4 such axes, it cannot be cubic, right? So do you know which direction the triad lies along in a cube? So along the body diagonal, right? And there are 4 body diagonals, which are the 4 triads. If you do not have 4 triads, it cannot be cubic. So we call this the defining symmetry of the cubic class of crystals. If I can only find 1 triad, that cannot be cubic. Okay? That is in fact a trigonal crystal system. In order to have a hexagonal system, hexagonal unit cell, I must have 1 hexad, with a rotation of 60 degrees, reproducing everything. Yeah? So when you look at the shape of a large crystal, and you can see along the body diagonals of that crystal and see that there are 4 triads, you know that it's cubic. You don't have to do any diffraction experiment. And similarly, if you can find a hexad, then it has to be in the hexagonal class. it cannot be in any of the others because none of the others have a six-fold rotation axis. So just by looking, all these crystal classes were derived not by diffraction, but by looking at the shapes of macroscopic crystals. Just came back last week from Russia, where I was visiting a minerals university, and I took hundreds of photographs of minerals which are on my website. And you can see the shapes of these very large crystals which have grown in nature over very long periods of time. Just by looking at those, the crystallographers derived the 14 Bravais lattices and the crystal classes and so on, with no reference to diffraction theory. Okay? Okay, so these are our 14 crystal classes. We have cubic P, F, and I. Then we have lower symmetries, and you've got the orthorhombic system where the three edges are all different in length, but the angles are all 90 degrees. And the lowest symmetry is the triclinic cell, okay, where none of the edges are equal and none of the angles are equal either. And this is a much simpler way of looking at those 14 as structure projections rather than the three-dimensional cells. Is everyone happy with that? Okay, so I've taught you enough for you to complete quiz 1. Okay? And please do that, because you will be able to see what you don't understand. Because, you know, sitting in a lecture, I'm telling you what is right and what is wrong, but you cannot test yourself until you actually try the quiz. Okay? So the purpose of the quiz is not simply to give you a mark at the end of the course, but so that you follow the lectures as we progress. And the second lecture then is not more difficult than the first lecture. Okay? Okay, so we will stop here today and see you tomorrow.